let's get started. Okay, this is hour 3 for Physics 1C, and we're going to be looking at this problem right here to kind of apply the knowledge that we learned about these series circuits. Okay, so we've got some information given: resistance, inductance, capacitance, voltage, and we're supposed to go through and find all of these things. So what I'm going to do is I'm just going to have you all do these calculations. I'm just going to kind of write down what they are. Okay, so XL, that was the one that was equal to omega times L. These problems are, by the way, very plug and chug. We have a lot of relationships that we're going to use. So omega L, so we've got 10,000 times L, which is 0.06 henries. So that's pretty easy to do, isn't it? It's just going to be 600. Yeah. Again, the unit is ohm because Henry is an ohm times a second. Radians never really show up in your answers, but there we go. That's XL. We also want to find XC. XC is the inverse of omega C. So this is equal to 1,000, sorry, 10,000 multiplied by C, which is, so it's 0.5 micro, so that would be 0.5 times 10 to the minus 6th. And then we need to take that whole thing and invert it. So we'll do to the negative 1 power. How easy is this one to do? This is 1e4, 1e minus 6. So that's 1e minus 2. 200, that sounds about right. Now we need to find the impedance or impedance. So above we said that Z was defined as the square root of R squared plus the difference between XL and XC. Got to square that difference. And then you got to square root the whole thing. This will be equal to, R was 300. So it's going to be you get 500. Yeah, this is pretty easy to see why you get 500. It's 300 squared plus 600 minus 200, that's also squared, and so you can kind of see there's this 3, 4, 5 triangle thing happening here, and you get that Z is equal to 500 ohms. Okay, the current amplitude I. Here's the first one where you have to actually maybe use a little bit of brain power. How do you find the current? How do we find the current? What could we do? How can we find the current? V equal IZ, that's exactly right. So the maximum voltage in the system, V, is equal to I times Z. So this means that if I do V over Z, V over Z, that we get I. Again, this is going to be I max. So our voltage was given in the problem as 50 volts. And we divide that by Z, which is 500 ohms. And so we get 0.1 amps. That's the maximum current. Okay, what's next? The phase angle phi. Phase angle is given by, there's two different expressions we can use. We could try both of them. One of them would be you take the arctan of XL minus XC, and and this is a C. XL and XC, they kind of look the same. And we divide this by R. This one would be, looks like 400. Oh, whoops. So this would be the arctan of XL minus XC, which is 600 minus 200. And then divide by R, which is 300. What does that give you? We'll do an answer in degrees and radians. What's that equal to? In degrees, I'm willing to bet it's 53 degrees. Yeah. And in radians, 0.93, that sounds right. Is it 0.932? Oh, 0.927. Okay, let's write it down with 3 digits just to... Do other people agree it's 927? Should I check it, or... We want the radians one, but... It's good to know, like, in degrees what it is, because you see radian measurement, you don't really know what that means, but if you say 53 degrees, you kind of get an idea of what that means, right? And there we go. Finally, we want to find the voltage amplitude across each element. Let's use the white space that's left up here to do that, and just write in a different color. The other method for finding the phase angle, if you want to do it, would be we would take the inverse cosine of R over Z. So that would be the arc cosine of 300 over 500. And you get the same answer for sure. You can check, though. All right. So finally, we want to do the voltage amplitude across each element. So this is where we need to say VR is IR. VL is I times XL. And VC is I times XC. Now, every one of these pieces of information is already given. So should I write what you plug in, or should I let you just plug it in yourself? Maybe it's more educationally valuable if you just plug it in yourself. So tell me what y'all get. What do you get for VR, VL, and VC? Maybe a few of you try VC, a few of you try VL and VR so we can get all the answers. You can put your answers in chat whenever you have them. You don't need to wait in this case. These are pretty simple calculations. So we've got current, and we've got, resistance, XL, XC. So. $30, okay. VC's 20. Nice round values in this problem. Oh, it's gonna be 60, right? Yeah. And there we go. Now, while these problems can be, I don't know what the word for it is, there's a lot of answers. You may have some problems on this homework where there's like 7 answers. They're all really easy to find, and I hope this homework doesn't trouble you too much. I think you should be able to figure most of it out. There are going to be some somewhat tricky things that I will try to reference later on. All right, so that's the first half of the problem. Anyone have any questions? Okay. The next thing says, we want to find expressions for the time dependence of the instantaneous current, the instantaneous voltages across the resistor, the inductor, the capacitor, and the AC source. So, to do this, we know VR is equal to big VR times the cosine of omega t. And we know the voltage across the capacitor is going to be equal to VC times the cosine of... Now, this is where we have to input the information we learned from the phasor diagrams. For the capacitor, it was... Should it be plus or minus pi over 2 for the capacitor? Do you remember? Minus, that's right. And then for our inductor, VL is just going to be big VL cosine of omega t plus pi over 2. Right? So what are these equal to? So we're going to get VR as a function of time is going to be equal to, I think big VR was like 30, right? Yeah, 30. Let's go ahead, let's write these down in a line here. So this was 30 VL, because this way we don't have to keep going back up. VL was 60, and then I kind of did it out of order, but so VL is going to be 60, and then VC is going to be 20. Okay. Okay, so we got 20 volts, and then we just need to multiply by the cosine of omega t, and omega was 10,000 in radians. Um, 10,000 plus pi over 2. And forgive me for not writing the units on these. There's just not a lot of space to do so. But there are radians per second on all these units here. There we go. And what's left? Voltage across the source. This is the one where we can actually use our value for this, because the voltage across the source is equal to big V, 50 volts, times the cosine of omega t, and now we have to... Is it add phi? We add phi, right? Yeah, because when phi is positive, it's ahead. It's okay, yeah. There we go. And so in this case, that would be equal to 50 volts times the cosine of 10,000 t plus 0.927 radians. There we go. Those are our answers. You guys got 927, really? Why did I write down 925? Let me see something quicker. Yeah, I agree. It's 927. I don't know what I wrote down in my notes, but there we go. Anyone have any questions? It's pretty easy, right? It's pretty easy. Well, I guess we move on to talking about power. I didn't think we'd get this far, but that's what we'll do. So we'll talk about power, and then hopefully there's enough time left over to do one more problem. Okay, so as far as power goes, the book goes through quite a long discussion about the way that power works when there's a resistor, the way that power works when there's just an inductor, and the way that power works when there's a capacitor. And while I think it's kind of interesting, I mean, I find pretty much anything to do with physics interesting, I don't know how educationally valuable it is to present in lecture form. I will say that when we think about in general what they do is the following, and I think you can kind of sum up most of what they talk about by just considering each of the elements themselves and how they behave in the circuit. So first of all, if we remember that resistors are basically just like light bulbs are a good example of a resistor, then you can kind of understand that every time that the current passes through the resistor, that there's going to be energy that's dissipated away from the circuit. And it could be in the form of light or heat or anything like that. And that the way that the resistor behaves is pretty much just as it would normally in a circuit. And the power for the resistor is just going to be... Do you remember what the power for a resistor is from DC circuits? For DC, do you remember what it was? What was the power for the resistor in a DC circuit? It has square in it, right? You don't remember it all? I know that you're not a generation that likes to memorize things, but certainly someone remembers. What's the power for a resistor in a DC circuit? It's okay if you need to go look it up. I squared R, right, exactly. I squared R. That's really interesting because this is actually the same answer we're going to get when we talk about the power in an AC circuit. So we need to understand something about the inductor and the capacitor. So with the inductor, what I would say is that there's going to be times when the inductor is being charged up, and there's going to be times when the inductor is being discharged, basically. So in one case, the inductor is basically going to have a positive power associated with it when it's delivering energy. The power from the source is going to be positive if the source is delivering energy to set up the magnetic field. And when the power is negative, the magnetic field is going to be collapsing, so the inductor is basically returning energy to the source. So for the inductor, half the time it's going to be positive and half the time it's going to be negative. It's going to be positive, so I should say the power. The power for the inductor is going to be positive when the source is delivering. The best way to say it's when the magnetic field is building up. Can I just say source is delivering? So the source is basically delivering power, and we call that positive. And that power gets built up into the magnetic field of the inductor. It's negative when the magnetic field is basically decaying. And the thing is that if it's a true inductor, that the sum of this over time is that the power for the inductor is 0 on average. Does that make sense? Half the time, the circuit is sending energy to build the magnetic field, and half the time that magnetic field is sending energy back into the circuit. So they kind of balance out. I mean, it's a sinusoidal function after all, so that's part of the reason why. The power for the capacitor is exactly the same. Half the time it's positive and half the time it's negative. It's going to be positive when the capacitor's charging up, and it's going to be negative when the capacitor's discharging. So this is positive when charging up, and it's negative when discharging. And if you sum those up, you get that the power for the capacitor, whoops, didn't mean to write it like that. You get that the power for the capacitor is equal to 0 on average. Half the time, it's acting as a sink for power while it's charging. Half the time, it's acting as a source for power while it's discharging. And on average, they average to 0. Okay? So what happens when we put everything together? Now, this is where we can kind of save ourselves a little bit of time by skipping over the details of how they go about this. The way that they go about describing all this in the textbook involves a lot of sines and cosines and a lot of trig and whatever. We're going to do that, but the point is that we can do it without doing it for every single piece. We can just do it for the system as a whole. So what we learned in the earlier chapters was that power was basically equal to current times voltage. So for us, we're going to get a power that's going to kind of vary as a function of time, because the current as a function of time and the voltage as a function of time are no longer constant. So this is what we got for DC. For AC, the power is going to vary as a function of time. And we need to plug in our functions here. So let's say that the power as a function of time now is going to be the current. Our current was defined as I times the cosine of omega t. We're talking about the entire system now, so we're going to be talking about the voltage across the source. That was the one that was V times the cosine of omega t, just like what we have written right up here, plus phi. That looks weird. And then what we can do is we can look at the fact that we have a cosine times a cosine here. And what we're going to do is we're going to use this. We're going to use this cosine sum formula, the one that says that if I have cosine, I can barely read it in my notes, it's so tiny. Cosine of a plus b is equal to, it's the one that's cosine, right? Yeah. Cos A, cos B, minus sine A, sine B. All right, so let's do that here. That looks right to y'all? Great, okay. All right, so we got power as a function of time is now going to be, we've got I times V. Pull those on the outside. I guess it's really just going to be this piece that we're going to expand out. So we'll have cos omega t. That's this one. And we'll multiply this by whatever we get here. So we're going to get cos omega t again. Cos phi. I'll just put parentheses around the omega t's. And then minus, we'll have sine omega t. And then sine phi. And then we multiply these through. The first term has cosine squared omega t times the cosine of phi. The second term has minus cos omega t this times sine omega t, and then sine phi. That's our power as a function of time. But what we really care about is the average power that's delivered. The oscillations in these circuits are going to be happening so quickly that on average, these power fluctuations are going to kind of dampen out, average out, however you want to put it. And what we end up caring about is just the average power. Well, how do we find the average power? To find the average power, we basically need to average these functions here, okay? We need to average these functions. But the thing we notice is that if we take and we average this function either from negative infinity to positive infinity, or we average it over one cycle, that this is going to give us 0. It's going to give us 0 because it's a cosine times a sine function, so half of the function is going to be above the line, half the function is going to be below the line. To find the average value of a function, you need to integrate that function over a period, and if you integrate this function over a period, you're always going to get 0. That makes sense? This one, though, cosine squared, this one's always positive. It's always positive. The cosine squared function is one that looks like, I think it looks kind of like this, right? If I remember correctly. Maybe not exactly like that, but something like that. So this is always positive, and we actually calculated right at the beginning of class that when you average the cosine squared function, you basically just get a half, right? Let me go back real quick to what we did right at the beginning of class. When we were talking about RMS current, there we go, you'll notice that we were looking at this function cosine, And what we said was we square it, and then we averaged it. And we averaged it, we actually just got a half multiplied by the coefficient right here, I max. So the average value of cosine squared over one period is a half. I think that's one of the things that Ash had mentioned earlier in class. So we'll get IV divided by 2. Here, let me put in here that this is equal to a half, just so it's really clear what we're doing. So this gives us a half. So what that means is that our average power ends up being IV over 2 times the cosine of phi. Or, the thing that's interesting about this, if we remember our definition, that IRMS was equal to the max current divided by square root 2, and VRMS was equal to the max voltage divided by square root 2. Well, these two are divided by 2, but of course we could replace that 2 in the denominator there by square root of 2 times square root of 2. So this would be like over square root of 2 and then over another square root of 2, which means that our average power then would become just the RMS current multiplied by the RMS voltage multiplied by the cosine of phi. And that's our first definition of what the average power is. You take the RMS current, you multiply by the RMS voltage, and you multiply by cosine phi. So now you might see why it's called the power factor, because it shows up right here. The smaller the value of phi, the bigger your average power output's going to be, right? If phi is 0, then you get the maximum power output. Something I wrote down here is, when the phase angle is large, cosine phi is small, and a large current is needed to supply power. Now, we can actually write this in a slightly different way. If you remember from the derivation we did a second ago, what was cosine phi equal to again? Someone want to remind me, what was cosine phi equal to? R over Z. That's right. R over Z. Z is always bigger than R, if that helps you to remember this, right? Because just if you look at what Z is the square root of R squared plus XL minus XC squared. So Z is guaranteed to be bigger than R, right? Guaranteed, because this is like 3 sides of a triangle thing. Of a right triangle, I should say. And the hypotenuse is always longer than the legs. So if we plug that in here, this turns out to be something kind of interesting. So now if we plug that in, we get that the average power is equal to IRMS times VRMS multiplied by R over Z. Oh, but look, there's VRMS divided by Z. What was that equal to? What's VRMS over Z equal to? In terms of units, it's voltage divided by resistance. So this is IRMS. This is the current. It's the RMS current. Remember, this is your big equation that we've. If you take anything else away from tonight, that's it. This is the kind of big thing that we kind of got to tonight. Voltage in an AC circuit is equal to I times Z, and you can always replace this with RMS if you want to. It still works, right? So VRMS. So then all of a sudden, this thing becomes. I'll go down one line. All of a sudden then, VRMS over Z is IRMS, then basically your average power, we're right back to where we were with DC circuits. It's I squared R. However, one caveat, you have to use RMS current now. This is only true for RMS current, right? This is AC power. Now, they're synonymous statements, right? But I like this one better because that cosine phi thing, it kind of like... Maybe your brain glazes over because, first of all, there's a cosine, so now you got to think about, like, what is the cosine, right? And what are the values that it could be? And then there's the angle, and you're like, what was the angle again? You don't remember. But if I just tell you that it's the RMS current squared times R, I think you could say that kind of makes sense, right? It's exactly what we got out of the DC circuit. And as we said from the very beginning, The way that this resistor acts in an AC current circuit versus a DC current circuit is exactly the same. It doesn't care that the current's flowing back and forth. There's current flowing. That's all that it cares. And the rate at which that current flows, squared times its resistance, is the power. This also shows you that what we said a second ago is true, right? I said that on average, the inductor doesn't do anything for the power. On average, the capacitor doesn't do anything for the power. And lo and behold, that's what this equation tells us, is the average power has nothing to do with the inductor or the capacitor. Although if you look at this equation, it kind of does. Sorry, this thing's lagging again. Yeah, if you look at this equation, you know, baked into that cosine phi is something about XL and XC. And technically, I'm lying to you a little bit because baked into IRMS, right, is the impedance as well, right? So it's in there. It's just not, it doesn't show up in this final answer here because, well, yeah. All right, does anyone have any questions? Any questions? I thought I had a good problem for this here. I think I have to go to the lab manual to find this problem to help you out. Yeah. Root mean square. It's the way of averaging things that are equally positive and negative, right? Because, otherwise they would average to 0. Does that make sense, Pui? The place that I was first exposed to them, and if you take the Physics 1 series in order, you would first be exposed to these in Physics 1b, where in Physics 1b what you're trying to describe is the velocity of gas molecules, okay? And if you think about the velocity of gas molecules in a room, if you were to average them, if you just average all the x components, half of them are going to move to the right and half of them are going to move to the left. So your answer would be 0 if you averaged all those velocities. It's kind of useless, right? And the same thing would be true if, oh, you talk about in chemistry 1A2, that's great. If you think about the y velocity of the gas molecules in the room, on average, half of them are going up and half of them are going down. So by averaging that out, you're also not really learning anything. However, if you average the velocities squared, you can get a good idea of what the average velocity squared is. But then you think, well, what do I care about velocity squared? Let's square root that. You square root it, you're back to something that means something to you. It's kind of the average magnitude, if you think about it, of the velocity of the particles. Does that make more sense, Ty? This is the average magnitude of the current. Does that make more sense? If you don't care about the negative signs, it's not exactly that, because you're averaging the squares and you're square rooting it, so it's not exactly the same thing as taking just the average of the absolute values, but it is kind of more representative. And absolute value functions are kind of not very well defined, right? Whereas squared functions are easily defined, right? We were able to do all kinds of stuff with them today. I mean, we basically did something here. Yeah. So, yeah. So I'm going to I'm just going to pull up the lab manual book. And I think, yeah, maybe we will. Maybe we'll just stop right there. The next things to talk about, there's really just hardly anything left to talk about. There's one more example problem. We're going to talk about resonance, and then we're going to talk about transformers, and that's it. And that'll only take us not very long. I can't finish it all right now, but we got to leave something to do on Thursday, right? So I think it's, I'm going to stop now for, lecturing, but I'll stick around if you guys have questions. I know some people had questions about the homework. I tried to address them in the homework channel, but for now I'm going to stop the recording.